Benvenuti a Catania, è veramente un onore avervi tutti qua. L'ultimo 2016, l'ultimo Macrogiovani fu nel 2016, ma eravamo ben più pochi. Questa è un'occasione veramente speciale perché è il 25° anno di Macrogiovani, quindi siamo veramente bello, soprattutto per chi in questo progetto ci ha creduto e continua ancora a lavorarci. Prima di tutto, sicuramente dimenticherò qualche cosa, ma prima di tutto volevo ringraziare chi ci sta ospitando, e quindi il professore Liciardello, che sono l'ultima volta che sono stata in questa aula scendevo le scale per laurearmi. La mia storia è nata qui. Il primo anno che ho partecipato a Macrogiovani, nel 99, uscivo proprio dal dipartimento, ero al primo anno di dottorato di ricerca, e il fatto che ancora tutti credino in questo evento è veramente incredibile. Quest'anno, proprio per questa particolarità, si è deciso di allungare Macrogiovani. Come sapete, ogni anno Macrogiovani dura circa 2 giorni, quest'anno invece siamo a 3 giorni e il riscontro da parte vostra è veramente grande. Ci saranno le solite presentazioni suddivise per tipologia di studenti, quindi studenti borsisti, però non hanno compiuto organizzato tutto parti d'Italia, perché il comitato organizzatore di Macrogiovani parte da Trento per arrivare giù in Sicilia, e in modo particolare l'organizzare in quanto fondatore di Macrogiovani. Ovviamente insieme ad altri colleghi che attualmente non sono presenti.
Beh, la scenetta dello zoppicare, perché non è che zoppico, ma perché i polimeri invecchiano e invecchiamo anche noi. L'aging, c'è iniziato questa cosa 25 anni fa a Gragnano. Come? Diciamo così, come? La settimana, solitamente dopo c'era comunque un evento, era l'EUPOC e via di seguito, ci ritrovavamo a girovagare, tanto ormai eravamo a Gragnano, in quel posto, stavamo lì sabato e la domenica, i ragazzi, perché poi partecipavano anche all'EUPOC. Allora ci siamo detti, ma perché non facciamo qualcosa? In quel fine settimana, in un momento in cui eravamo ci conoscevamo di noi. Allora ho detto, perché non iniziamo a organizzare un evento, diciamo, pseudo-scientifico, in cui tutti i ragazzi si presentano, parlano fra di loro, si presentano, fanno chairman, organizzano l'evento, in maniera tale da... E lì è partita, in maniera quasi scherzosa, eravamo tutte, tra virgolette, dei monometri, perché lavoravamo separati in maniera di quelle italiane, ma non solo, perché c'era qualche collega che veniva anche da fuori, che faceva il dottorato fuori, eccetera, ma non eravamo uniti, non ci conoscevamo. Allora avevamo una gran voglia di legarsi in catena principale. Molto in questa sala, ok? Anche se giovani in teoria è un momento di grazia che passa molto velocemente, però ci continuiamo a sentirci giovani anche per questa iniziativa dell'AIM, voluta poi comunque, perché poi abbiamo trovato nel direttivo dell'AIM di allora, ma poi si è ripetuto nel corso del tempo di questi 25 anni, detto ma che bella, è una bella iniziativa, la passiamo. Eravamo a Gargnano a spese dell'AIM perché pagavamo la quota associativa, ma ci tenevano su, stavamo ospitati via di seguito, ma perché avevamo dimostrato già allora, scusate, apro una piccola parentesi, poi se sono prolisso mi fermi, però volevo fare un minimo di storia. A quel punto nacque anche giovani, c'è sempre gente che si rinnova. Ci sono 60 postdoc, giovani comunque, che sono tutti qua per fare poi avremo tempo in questi giorni di conoscersi meglio e spero e scientifiche poi, perché saranno quelle che vi porteranno nella vita dei legami talmente forti fra di noi, e che noi li abbiamo, ok? Che aiuteranno tutti a crescere in questo sistema paese. Grazie.
Bene, poco da dire. Veramente importanti e quindi sì, insomma, vedere gli amici, i colleghi è un piacere, e vedere poi comunque i ragazzi che noi conosciamo, perché comunque lavorano nei nostri laboratori, quindi anche questo è un piacere. E Catania è sicuramente, come appunto come un luogo proprio nostro, cioè il Palazzo Feltrinelli era un pochettino tornare ogni anno, riconoscere la stessa camera, riconoscere il luogo che si passava, la spiaggia dove si andava a prendere un po' di sole quando era sempre anche piacere di sede, anche quelli diventeranno dei passaggi un po' buoni, il 25esimo ce la godremo, siamo venuti per godercela, per stare insieme, per chiacchierare, magari anche di lavoro, ma sicuramente per godercela, e voi che lavorerete in vi auguriamo di stringere rapporti e godervela anche voi. Okay.
Bene, Buonasera a tutti, io ho chiesto di venire a fare questo benvenuto, l'ho fatto molto volentieri, perché è sempre un grande piacere per noi che ormai tanto giovani non siamo, in particolare io, che qua è il mio collega di corso Domenico Garozzo. È un particolare piacere vedere tanti giovani e giovanissimi colleghi, diciamo, cimentarsi in un meeting scientifico che credo sarà anche di alto livello, perché senza voi giovani ovviamente non andiamo avanti. Sono ancora di più contento di partecipare, per darvi il benvenuto a questo evento, perché pur non essendo un macromolecolare, non essendo quindi un macro vecchio, un macro giovane, diciamo ho avuto qualche volta, il professor Mondaudo qualche anno fa mi invitò a un piccolo intervento in uno dei nostri della IMA normale, quindi qui a Catania, credo una quindicina di fa, do ancora un caldo benvenuto, caldo proprio anche, vabbè. A pochi giorni proprio scientifico anche alle regole di orientali che
vi do il benvenuto anch'io sono da questo è la prima volta che sono da questo con il professor Ricciardello.
eravamo da quell'altro lato il giorno della laurea.
Fare i complimenti agli organizzatori per organizzare intanto per l'idea, come hai raccontato tu, e poi per riuscire ad avere dopo così tanti anni sempre numeri così grandi, sono notevoli, e io penso che questo sia utile sia a noi vecchi sia soprattutto ai giovani, che quando si incontrano tra loro riescono a essere anche produttori di nuove idee, di nuove iniziative, e spesso hanno più iniziativa e più voglia e più fantasia rispetto a noi. Quindi vi auguro di nuovo buon lavoro e vi faccio di nuovo i miei complimenti.
Come detto, qualche cosa l'avrei dimenticato, forse ho dimenticato la cosa più importante, il fatto che il nostro presidente, il professore Michele Laus, non è potuto essere presente a questa iniziativa a cui tiene veramente tanto, e ovviamente vi dà il benvenuto e un forte in bocca al lupo per le presentazioni. Come saprete, le presentazioni le più belle, le più interessanti, ci saranno delle varie giurie e ci saranno dei premi, quindi questa è un'altra chicca che come associazione ogni anno ci pregiamo, insomma, di dare. Nelle commissioni, perché voi sarete farete parte delle commissioni. Ragazzi, fanno un bel applauso. Il Carlotti. Bene, è ora di partire. Lasciamo il posto ai chair e noi di commissione in prima fila.
The students, I have the pleasure to introduce Sara Alfano with her works on sustainable chemical modification of polydroxyalkanoates. So, yours.
Grazie. So, good afternoon. Thanks for your kind introduction. Today I will show you our strategy to achieve a sustainable chemical modification of polydroxyalkanoates. PHA are a class of biodegradable polyesters produced in microbial cultures starting from local feedstocks. They are characterized by similar properties to that of polyethylene and polypropylene, and for these reasons they are the potential substitute for fossil plastics in the fields of disposable objects and packaging. In addition, PHAs could degrade in physiological condition into natural metabolites. This is the key factor explaining why they are non-immunogenic, biocompatible, and bioresorbable, allowing them to be easily incorporated into biological systems. Recent advances in processing demonstrate the high potential of PHAs to be used as a base material in many biomedical prototypes, including soft and hard tissue engineering and drug delivery and the fabrication of implantable devices. However, the high hydrophobicity and the lack of functional groups could limit their stability in physiological conditions and therefore their real applicability. For this reason, chemical modification of PHAs are needed to tune their hydrophobicity and make such materials a valuable alternative to synthetic polymers. Unfortunately, toxic solvents and reactants are used for polymer functionalization, resulting in several purification steps and in the loss of the advantage of using a biomaterial. So how can PHA's applicability be improved without losing the ecological benefit? To answer to this question, we started this study about introduction of functional groups in PHAs using the aminolysis reaction and with the use of only safe chemicals. So our strategy is to replace the commonly used toxic amines with choline taurinate, which is a ionic liquid soluble in water and ethanol and that does not show cytotoxicity. The use of choline taurinate leads to introduction of a sulfonic polar group in PHA structure and to an increase in their wettability. Additionally, aminolysis usually is carried out in methanol, so we used it just as a reference with the aim to replace it with ethanol and water, which are considered green solvents. So, Casted films of polydroxybutyrate cohexanoate were first of all thermally annealed and then aminolyzed at 60 degrees for different contact times in the selected solvents. Spectroscopic characterization highlighted that alcoholic solvents are good solvents for aminolysis since the typical amide peaks are clearly visible, while no changes are detected when water is used as a solvent. These observations were also confirmed by contact angle measurements with decreasing values for samples aminolyzed in methanol and ethanol and quite constant values for samples aminolyzed in water. These results leads us to conclude that water is not a good solvent for aminolysis since the amino group of choline taurinate is protonated and resulting in no reactivity for nucleophilic substitution. Analyzing more in detail the trend of contact angles as a function of reaction time, it's possible to note that for higher times, wettability remained constant instead of increasing as we expected, and films became too fragile to be handled. So to understand what happens to the surface and to find an explanation to this behavior, morphological analysis has been conducted. Scanning electron microscopy highlighted the appearance of lamellar structures, probably due to the erosion of the amorphous surface layer. And the hypothesis is that by pushing the reaction to higher times, the degradative nature of aminolysis prevails, with a consequent surface etching and the release of oligomers in the reaction mediums. To verify this hypothesis, the reaction mediums has been fractionated through selective solubilization, and 3 different fractions were collected. The first fraction were collected in chloroform and is composed by aminolyzed long chain, while the second fraction was collected in ethyl acetate and is composed by aminolyzed short chain. In fact, in the reported FTR spectra, it's possible to note that for the second fraction, the intensities of carbonyl absorption of ester bonds and of amide peaks are quite the same. Finally, the third fraction was collected in ethanol and is composed by aminolyzed monomers. In fact, it's not possible to detect any absorption of ester bonds. The second fraction resulted to be the more interesting, as could have amphiphilic properties and could be used as a surfactant. For this reason, it was used for the preparation of an oil and water emulsion, which allowed us to obtain nanoparticles. Since these nanoparticles could be useful for the hydrophobic drug delivery, encapsulation tests were carried out using unique acid as a model molecule. So in conclusion, this work demonstrated the possibility to obtain a sustainable chemical modification of PHAs and to broaden the range of PHAs applicability in biomedical fields. Of course, this strategy should be improved, and further studies will be conducted to optimize film's functionalization and to optimize also the encapsulation efficiency of nanoparticles. I would like to thank the organizing committee, my research group in Rome, the LAMP group, and all of you for your kind attention. Thank you.
Thank you, Sarah, for your nice presentation, and I will ask if someone Okay, so I have 2 questions. You if you need a purification step after your functionalization of the PHA, and if you already know the precise
Scusate, eccoci. Hi everyone. Just to give a brief introduction about my work, polymeric nanocarriers are usually synthesized from synthetic or natural polymers. In particular, as Sarah said before, like PLA, PCl, and PHA have been widely used because of their biodegradability in physiological conditions. However, however, they lack of functionalities in their backbone to improve cells' interactions. Stabilizers are needed to form nanoformulations in water, and loading efficiencies are quite low. So, promising alternative was found in the polyglycerol adipate, which has gained interest because of its biodegradability and biocompatibility in water, ability to form nanoparticles, sì, non è vero, in physiological conditions, ability to form nanoparticles in water without any surfactants, and possible functionalization by using its secondary hydroxyl group. So during my abroad period at University of Nottingham, in collaboration with Taresco and Audol Group, we synthesized 4 polyadipates by changing polyols from glycerol to diglycerol, both coming from renewable sources, and adding hexandiol to modify the hydrophilic-hydrophobic balance in order to strengthen the encapsulation efficiency of hydrophobic drugs. Firstly, enzymatic polymerization of PGA and PDGA was carried out using Novozyme as catalyst at 50 degrees for 5 hours, and polymers formation was confirmed by proton NMR. As you can see, the vinyl peaks of the DVA disappeared in the polymer spectra, but also the adipate peaks were broader than before, further confirming polymerization occurrence. The same reaction conditions were used to synthesize the hexandiol-based polymers, and again, proton NMR was used to confirm hexandiol introduction in the polymeric chain. GPC analysis was performed to evaluate the successful polymerization, and as you can see from the table, PDGA showed a lower molecular weight compared to PGA because of the glycerol lower solubility in water, whereas hexandiol-based polymers showed higher molecular weights because of hexandiol higher solubility in THF. All the synthesized polymers were amorphous with glass transition temperatures below minus 20 degrees, and their wettability was evaluated by contact angle measurements. PDGA showed the lower contact angle compared to PGA because of its higher hydrophilicity, and the same trend was found for hexandiol-based polymers. Then nanoparticles were prepared by nanoprecipitation method in water, forming narrow dispersed nanoparticles with sizes between 120 and 150 nanometers, and the zeta potential was negative for the prepared nanosystem, and this was highlighted for PDGA-based polymers because the presence of more hydrophilic hydroxyl groups led to the formation of a more stable hydration shell which interacts better with water. Sizes and shapes were also were confirmed by TEM. Biological stability of the nanoparticles was evaluated by incubating each suspension in a solution of bovine seroalbumin used as a model protein at 37 degrees. Hexandiol-based polymer sizes were pretty much the same, and in particular, PDGX nanoparticles were the most stable because the hydration shell creates an efficient steric hindrance against BSA. Moreover, cytotoxicity was evaluated both in vitro and in vivo on Caenorhabditia elegans, worms belonging to nematodes phylum. And as you can see from the video, after 24 hours, nanoparticles did not show any toxic effect compared to the blank, therefore corroborating their biocompatibility in vivo. Their ability to encapsulate hydrophobic molecules was evaluated by co-nanoprecipitation method of polymer with coumarin-6 used as a model drug. And after the encapsulation, sizes were in generally higher than before, and the zeta potential was still negative. And the apparent solubility of coumarin-6 was measured by UVVs and calculated using this equation. And all the polymeric nanoparticles were ranked according to the delta A percentage value. Hexandiol-based polymers showed an increase in the apparent solubility of coumarin-6, which was especially higher for PDGAX nanoparticles. In the end, in vivo uptake of coumarin-6 was evaluated on hexandiol-based nanoparticles following the transport of coumarin-6 through biological membranes. And as you can see from the fluorescent images, the nanoparticles were all taken up after 24 hours, allowing us to use them as a possible nanovehicle for hydrophobic drugs for future studies. So I want to thank the organizing committee for giving me the possibility to show my work, my research group from Sapienza University of Rome, the collaborators at University of Nottingham and Paris. And thank you for your kind attention.
Thank you, Benedetta, for your nice presentation.
We did that with the BSA, just on using
your polymer precise molecular weight for the nanoparticle, or
no, we just we didn't even purify the polymers, so the GPC traces also showed oligomers peak, but it was okay for our.
on wound dressing based on functionalized and cross-linked chitosan. The stage is yours.
Hi, I am Clarissa Ciarlantini, a PhD student from University La Sapienza, and today I will speak about the development of antioxidant wound dressing based on functionalized and cross-linked chitosan. Wound healing is a process based on 4 steps, but if in an organism are present some local or systemic factor, this process can be blocked in the inflammatory phase, and this can lead to the formation of chronic wounds. Researchers try to develop a bioactive dressing that have to allow the correct regeneration of this injury. Bioactive dressing have to be biodegradable, biocompatible, possess antimicrobial properties, balance the release and absorption of exudate, maintain the correct level of oxygenation and the temperature, and in the end, possess all the chemical-physical properties necessary for the skin regeneration. Among the material that we can be used in the production of this dressing, Polysaccharides are highlighted thanks to their bioactive, biocompatible, and biodegradable properties. One of the most used is chitosan, that is a polycationic polymer with good antimicrobial properties and that can speed up the wound healing process. However, it presents poor dimensional stability in aqueous medium and mechanical properties not suitable for the wound healing application. For the reason, different strategies have been developed. In the first case, we have the possibility of cross-linking chitosan through the use of covalent or ionic cross-linkers. In the second case, we can create a complex through the interaction between chitosan with an anionic polymers. And in the third case, we can create a nanocomposite material through the introduction of nanofillers in the chitosan matrix. In our case, we decided to create a bioactive dressing using a cross-linking process. In fact, chitosan was initially modified with the glycidyl methacrylate, named the GMA. The reaction conditions are reported below, and this modification was taken into consideration because we want to introduce a double bond in the chitosan chain that is necessary for the subsequent cross-linking process. In the second phase, we decided to introduce glycerol, named GLI, as plasticizer at 3 different concentrations in order to see how this can modify the mechanical properties of our matrix. And as I said before, our matrix have to be cross-linkers, and for the reason we decided to use ethylene glycol dimethacrylate, named EGDMA. In particular, we decided to develop a surface cross-linking. In fact, our matrix was immersed in a solution of EGDMA at 3 different concentrations. In the end, to introduce antioxidant properties and to increase the antimicrobial properties of chitosan, we decided to introduce the 3,4-dihydroxyhydrocinamic acid, named ACIF, using 2 strategies. The first, using the inhibition process, and in the second case, we want to create a covalent bond between chitosan and our antioxidant using lacase as catalyst. To evaluate the introduction of GMA and GLI, FTR spectra are collected, and we can see the formation. In the first case, we can see the formation of new peak. In the first case, we have the stretching of the ester carbonylic group. In the second case, the stretching of CH relative to the double bond. These two are due to the GM introduction. In the case of GLI, we can see the formation of a third peak that is related to the CO stretching of the tertiary alcohol. Obviously, this functionalization modifies also the chemical-physical properties. In fact, we can see a decrease in the swelling capacity and in the contact angle associated with an increase in the water vapor transmission rate. Obviously, the introduction of glycerol caused a decrease in the elastic module, but only in the case of 20% of glycerol, we have the best elongation percentage. That is what we need for a good wound dressing. For the reason, we decided to apply the cross-linking process only on this matrix. Cross-linking process was evaluated through the use of thermogravimetric analysis that show an increase of thermal stability with the increase of concentration, and also a decrease in the swelling capacity of our dressing. What is more important to see is that only in the case of the lowest concentration of EGDMA, we obtain the best elongation percentage. For the reason, we evaluate the introduction of our antioxidant only on this matrix. The evaluation was due to the measurement of antioxidant activity against a model radical named DPPH. And we can see that in both strategy of introduction, we have an incredible decrease in the value of EC50. And also in the case of the evaluation of antimicrobial activity, we can see that with the introduction of antioxidant, we obtain percent of reduction around 100%. These results are really preliminary, but is really, really promising. To sum up, I want to say that the introduction of GMA and GLI increased the dimensional stability in a physiological environment, and the concentration of 20% allow to obtain a matrix that can be used in wound healing application. The cross-linking process allows to obtain the best deformation percentage only in the lowest concentration of GDMA, and in the case of ACF, we obtain an improvement of antimicrobial and antioxidant properties respect to chitosan used as standard. We have some work in progress. We hope to evaluate the cytotoxicity and the cell viability of our dressing. I would like to thank all of you and also the Istituto di Scienze e Tecnologia dei Polymerase that helped me with the evaluation of antimicrobial activity. Thank you.
Thank you for the nice presentation. I wanted to ask, maybe I missed this point, but do you have target mechanical properties for your patches? So a target elastic modulus, a target net break?
Yeah, we have thank you for your we have a target so per transmission we stay under the 30, 30, the value of 30, yes.
Okay, thank you. While the stiffness as a target? Sorry for...
No, also the thickness, but it's more important the ability to adapt our dressing to the wound, so to the reason. A lot of different concentration, but only this allows to obtain a value of swelling capacity that is we want. So
mechano-responsive nanofiber spinning of mechano-polymers blends. So the stage is yours.
Good evening. Okay, thank you. Good evening. Today I will share with you my work, which is related to mechanoresponsive nanofibers. So let's start from the concept of mechanoluminochromic polymers. These type of materials are able to respond to an external mechanical stimulus by changing their optical properties, especially their emission spectra. These materials can be prepared by including to the polymeric matrix a luminescent molecule. Of course, there are different luminescent molecules or dyes that can be used, and one example are the aggregochromic dyes. These molecules have the main characteristic that their optical properties depend on their state of aggregation. So they change their emission spectra depending on if they are aggregated or dispersed as monomer. So the main goal of this work is to be able to shift from the initial aggregated state to the dispersed monomeric form by applying an external force. So thus our mechanical stimulus. Well, this field was widely studied by Professor Vere's group at the Adolf Merkel Institute in Freiburg, and in the last years they developed this new type of aggregochromic dye, which is this telecalic macromolecule made by a short polymeric chain with two oligoparaphenolen vinylene molecules at the ends, which are the aggregochromic moieties. This telecalic was then blended with different polymeric matrices, and the final blend that they obtained were then tested to evaluate the mechanochromic response. They obtained great results, and they were due to the capacity of this telecalic to form entanglements with the chains of the polymeric matrix. So what's the novelty of our work? Because we use the same telecalic dye, the same polymeric matrix that is a polyurethane matrix, but we change now the processing of the processing of the material. We use the technique of the electrospinning. With the technique of the electrospinning, we were able to make these woven-non-woven materials made of nanofibers that can be dispersed and oriented in a random, with a random orientation or aligned parallelly, depending on the collector that you use during the process. So we made these two different morphologies of the material, and we test them to study their mechanochromic response. Here there is a short video of the electrospinning process where you can see that the starting solution have a green emission because of the dispersion and not aggregation of the dye. But with the formation of the fibers and the evaporation of the solvent, you can see how the fibers in the collector look orange. So how is the mechanochromic response of these materials? As you can see here, with increasing of the strain, increases in both cases the intensity of the monomer band. So we pass from the orange emission color characteristic of the aggregate to the green one characteristic of the monomer. And this transition, this color transition, could be observed in both the samples. Then we exploit the wavelengths, the one of the aggregate, the one of the monomer, and we calculate the ratio between the two intensities. With this ratio, we investigate how it varies with increasing of the strain, and we observed that the ratio increased linearly with the strain in both cases. But if we compare the percentage variation of the two samples, we can observe that the slopes are very different. In particular, that of the aligned mat, it's much, much greater than the one of the random. Especially if we observe the low strain values, we can see that at the same value of strain, the response of the aligned mat is 3 times that of the random one. And this result in a very different level of sensitivity of the two samples. In particular, the aligned one result more sensitive with respect to the random one. So to better rationalize this behavior, we study the nanofibers of these electrospan woven on woven materials. So electrospan thin layers of these nanofibers, we could analyze the change of the color of the fibers with increasing of the strain, passing from the orange to the green. But one detail that I want to highlight is that, as you can see, only the fibers in the same direction of the applied force change their color from orange to green, while the others that are oriented in a different direction remain with the orange initial emission color. And this is the explanation because we obtain these two very different responses with the two different morphologies, because only in the aligned mat we have all the fibers oriented in the same direction of the applied force, while in the random mat only a part of the fibers are oriented in the right direction. So, to conclude, this telecalic aggregochromic dye could be used to make mechanochromic polymers, which can be processed in with different techniques, for example, the electrospinning, and this technique allows us to study the anisotropic mechanochromism, with which we discovered that the line facilitates the mechanochromic activation at low strain values. Then we were able to study also the mechanochromism of the single fibers. I would like to thank the organizing committee for giving me the opportunity to be here. And I would like to thank also Professor Stefan Schertel and Dr. Dera Kibala from the Adolf Merkel Institute of Fribourg. And thank you all for your attention.
Thank you. Are there any questions for Valentina?
For the really interesting presentation. I have two. I was wondering if you can see anything also in the absorption spectrum of your materials, the fluorescence one.
Yes. In chemistry, we know that absorption experiments are very important, but when you work in the solid state with these non-homogeneous samples, it's very difficult to measure. Make quantitative, so we base it mainly in the emission spectra only.
Okay, thanks. Another thing was if you have checked the reversibility.
In the past studies with the films that the group of Professor Vedder published, they verify the reversibility of the matrix. With our fibers, it was quite complicated because during the analysis, when you are irradiating your sample, you have to be very, very careful not to bleaching your sample. So make reversible experiment, cycling reversible experiment results, but your reversibility, but only in the line one have a very short deformation, so it's very difficult to try the reversibility.
Very much.
I suppose we have another question. Yeah.
Thank you, Valentina. I was wondering if you studied the temperature effect of the strain on the responsive. Well, if you apply the stress in temperature like 0 and 40, so So that's all.
Thank you. Also, this one it's a complicated part because the polymeric matrix that we use has a very low room temperature. And if I overcome to the more of my fibers, I cannot go in a
I will introduce you Simone Donato, with based on liquid crystalline networks. The stage is yours.
Thank you. So good afternoon to everybody. Today I will show some results that I obtained in my PhD period abroad, made in Trinity College of Dublin, about the realization of microstructures made on liquid crystalline networks. Liquid crystalline networks are smart materials able to shape change their properties under an external stimulus that can be various. We can use light, temperature, magnetic, and electric field. Also, we were able to control the kind of actuation that we perform with our material thanks to the use of liquid crystalline alignment surfaces. So in this case, I was able to obtain contractions, but we can obtain also bending and twisting, as you can see by the videos that I report. I focus in my work on the realization of different monomer mixtures made by a liquid crystalline reactive, a cross-linkers, a dye, and a photoinitiator. And these kind of microstructures are particularly interested in the field of microrobotics, photonics, and microfluidics. But I was focused on the realization of systems that can be used in the encryption field. In particular, what I want to realize is to hide a letter inside an indistinguishable array when the stimuli is off, and then to reveal this letter under a particular kind of stimuli, so the encoding. So as first, the realization of microstructures calls for a new kind of lithography technique, and I was able to use the direct laser writing with 2 photon polymerization, in which a near femtosecond laser was deeply focused into the liquid crystal cells, and allows me to obtain the photopolymerization in only one spot of the liquid crystal mixture to obtain the final design that I previously performed. In this case, to obtain a well-shaped microstructures, I need to obtain a chemistry and a lithography optimization to obtain an improved morphology and the best actuation properties of the three-dimensional microstructures. So for what concerns the chemistry optimization, I propose the use of different monomer mixtures based on different cross-linkers, which possess different substituents in the liquid crystal core. Cause, as I previously stated, the substituents in the cross-linkers as the powerful tool to obtain huge modification in thermal, mechanical, and also the actuation properties of the final materials. As you can see by the DST trace, using a phenyl group in the liquid crystal core of the crosslinker, I was able to obtain a decrease in the glass transition temperature of the final material. But not only, because I have to also use a lithography optimization, changing the printing parameters, in this case laser power and scan speed, but not only, because I changed the height of the structures and also the structural design. As you can see by the first image, I started to produce micro blocks completely sticked on the glass. Then I moved to suspended structures, so a suspended block. And then I increased the complexity of the system, producing states with different steps. All these microstructures are thermally characterized under cycle of heating and cooling in order to demonstrate the contraction of the microstructures obtained and the reversibility of the process. But then I focus myself into understanding the changing of parameters in the printing, so the laser power and the scan speed, which kind of goal I can obtain. And I demonstrated that I can vary the actuation of the same material and the same microstructures, only changing the printing parameters. Then I made a comparison with the 3 different monomer mixtures that I performed in these studies in order to understand which is the best material in terms of actuation, but not only, also for the morphology. And the LCN6 with the funny ring as substituents in the liquid crystals core seems to be the best materials in terms of actuation and morphology. Once I found my best material, I start to produce this kind of arrays. So I want to hide an information that in my case is a letter inside an indistinguishable array. In this kind of work, I choose the binary encoding. So when the stimuli is off, you are not able to recognize the letter. Once I switch on the stimuli, thanks to the contraction of the different blocks composing the array, you are able to reveal the letter. So as first I started with a grayscale approach, which means that I change for one step of lithographic technique the contraction and the parameters for all the blocks. And in this case, I was able to obtain different contraction from the same material. And at 180 degrees, you can obtain and reveal the letter T, as you can see. But to emphasize the difference in contraction between the different pixels, I choose to use a multi-photoresist approach. So I combine the first lithographic technique with the liquid crystal mixture with another photoresist that is not able to contract under light or under temperature, which is the IPL. And in this case, the difference in contraction is more high. This kind of system, I demonstrated that can be used in the field of encryption, that is a physical encryption, not another one. In this case, we can obtain a system, so a device that cannot be attacked by the external, like with cyber attacks, and that can be triggered only with one stimulus. Then I inserted in my monomer mixtures also a die in order to demonstrate that I can obtain a multi-responsive material. In this case, as you can see, the array can be contracted under light, and the process is reversible and reproducible. So in this case also I performed a better system because the time scale changed from minute to second, milliseconds, we can say. So in conclusion, I can say that I performed chemical and lithography optimization to realize different microstructures made by liquid crystalline networks. All the microstructures were characterized thermally and also with light, and demonstrate the possibility to be used in the field of physical encryption, which is better from the cyber one. I would like to thank all my supervisors in this part, both from the University, the Trinity College of Dublin, and both from the University of Florence, and all of you for attention.
Nice presentation. Okay, I have a question for you. In your monomer mixture, you will also try to change. Don't do that.
So I choose to use this die for the technique. I use a laser with a wavelength of 780 nanometers, so I have to change the spectra of the die that I used, not like tails of absorption. In this case, I will lose element, and so I will lose contraction of the fine material. Now I can option that we can use, but for sure we will evaluate also other dyes for the future. Thank you.
Kind of a amazing, but once you know that the laser
for example, you have like a QR code that is only for you, and you only you.
Once you know the laser that activates the mechanism, you are done. You read it.
No, you have to use a particular power. Build the best difference in contraction from the pixel. I'm sorry, I don't care. No.
Nice.
Thank you.
Thank you.
Are there other questions? Okay, so thank you. Now it's the turn of Andrea Escher and his work on one-step fabrication of hybrid via the confined self-assembly of block polymers. Andrea, the stage is yours.
Hi everybody, my name is Andrea Escher and today I present my project at the Adolf Merkel Institute. And in particular, this project is focused on the realization of hybrid photonic pigments via the confined self-assembly of block copolymer. Before starting, I want to say that this presentation is divided in four main parts. We have an introduction, then we're talking about the project, the results obtained in the institute, and finally the conclusion. Before starting with the core of this presentation, I introduce the topic, and the topic is the color. Color is the visual perception based on the electromagnetic spectrum in the visible range, and most of the color are considered chemical color. But in this case, the color is obtained by the partial absorbance by chemical pigments or dye inside the matter. And here we have a very big problem because these kind of pigments are lifeless, dull, and also fading. But we are, in contrary, in nature, we have some example of very brilliant color. And in this case, we have, for example, the exoskeleton of bugs or the wings of butterfly, in which the interaction with the light and this periodic structure can make this very brilliant coloration. In this case, I report the image of this periodic structure, and this periodic structure is called the photonic structure. In this structure, you have two different materials with different refractive index and can be ordered in 1, 2, or 3 dimensions. The goal of this project is to realize photonic pigments using the block copolymer. And we want to obtain these photonic pigments because we have brilliant color that with metallic appearance, they are stable and also they are long-lasting. So, I've just said that we are interested in the use of block copolymer, and in particular we want to use block copolymer because thanks to their self-assembly properties. Using this diagram phase, we can predict the domain, the nanoscopic domain structure inside our pigments, and in particular, in our case, we are focused in the lamella structure. just controlling the volume fraction of the block copolymer. I report also a sketch of the block copolymer made with block A and block B, and I report also how obtain our photonic pigments by a simple 3D self-assembling in water oil emulsion of our block copolymer, and thanks to that we can obtain a spheric and concentric lamella structure like the example reported here in the slide. So for my project, I use two different D-block copolymer. The first one is made with polystyrene and polyvinyl pyridine, and the second one is made with polyvinyl pyridine and polymethyl methacrylate. The idea is to tuning the domain size of these pigments in order to tune all over the visible range my pigments. I report here the optics image taken with the microscope, and we can see that the color coming from to the violet to the red. And in particular, I report also this reflectance spectrum in which we have three different peaks that are associated to the photonic band gap. In this case, the photonic band gap is a region in which the photon cannot be propagated and was diffracted backwards. And thanks to that, we have the appearance of this brilliant color. The position of the photonic band gap is linked to the Bragg-Snell law, in which we have some different parameters, for instance, the domain size or the effective refractive index of the material. And in particular, in our pigments, we have two different materials, one with high refractive index and the second one with low refractive index. But in that case, we have a problem, and the problem is that the dielectric contrast is very low, and so the idea is to increase the dielectric contrast using a hybrid particle. I approach this problem in with two different methodology. The first one is called the increment of the electric contrast in situ approach. And the idea is to starting with a water emulsion of photonic pigments, changing the solvent from water to ethanol, and thanks to that we can promote the selective swelling of one of the two polymer domains, and also to promote the infiltration of metal ions inside in the solution. In this case, I use gold metal ions. I finally have the formation of the nanoparticle inside the pigments by or thermal treatment or chemical reduction. Here I report the primary results of this research project, and I have the reflectance spectrum of these pigments. The blue spectrum is the spectrum of the sphere without the nanoparticle inside, and the second one is with the nanoparticle inside. I collect also the image of the two different pigments, and I report also the Phoebe image. The Phoebe image was taken with the Phoebe microscope, which is basically SEM, with a focus ion beam inside, and thanks to that we can cut this polymer sphere, and we can see inside the lamella structure. In particular, we are interested in this primary part, in which the white dots are the gold nanoparticle precisely located in one of the two polymer domains. The second case is called the increment of dielectric contrast by ex situ approach, and we start with a solution of block copolymer in chloroform and another solution of quantum dots, this case in xentoluene. We mix together by emulsion process the two solutions, and we can obtain also for this case photonic pigments with inside the quantum dots. Also for this case, I want to report the primary results, and in particular we have this reflectance spectrum of the blue spectra is the one without quantum dots inside, and we can see that the photonic band gap, the peak is located between 400 and 500 nanometers. After the formation of the quantum dots, the photonic band gap shift to high wavelength, which was located more or less at 600 nanometers, and we increase also the reflectance of this sphere. Also for this case, I report the two images, the one without quantum dots and the second one with quantum dots inside. And finally, I report also for this case the Phoebe image, and we can see that we have a very good homogeneous distribution of quantum dots inside the polymer domain. So in conclusion, I obtain a very large spectrum of photonic pigments that come from to the violet to the red range in the visible light. We have prepared hybrid particle that are a very promising approach to increase the electric contrast of these photonic pigments. And finally, obtain also a very good distribution of the nanoparticle inside of one of the two polymer domains. For future development, we want to improve the size distribution of the sphere and also reducing scattering phenomena of these pigments. I want to thank my photonic group with Professor Davide Comoretto and Professor Paolo Lava, and in particular I want to thank a lot the Adolf Merkel Institute with Professor Ulrich Steiner and Dr. Andrea Dodero. So thanks you all for your attention.
Thank you, Andrea, for your nice questions.
For this presentation, only a curiosity, I wanted to ask, why did you use the golden particles, and maybe if you have tried another type of metal?
Yeah, we try different particles, especially with, of course, ion metals inside. I try with titanium. Pigments. For this case, with thanks.
First of all, thanks, Andrea. Pieces which are
of gold.
Yeah, sure. And it's more interesting the for metal inside the polymer matrix. Do you have a good reproducibility of the metals?
Yeah, approach the chemical and the structure. Reproducibility in large scale probably is better because you can obtain a very homogeneous distribution inside the sphere. The chemical one is it's a little bit.
Do we have another question for Andrea?
Which is the application of this?
Is to create paints to the idea is to create a sprite for
maybe the last question.
I'm sorry. Related to the question, which one of the approaches do you find would be best for like large scale and scale up applications?
Okay, the first one, of course, second one is not for industrial application, but in that case, the application is for so which is completely use the dots for other kind of application.
Anna Spinaguarin with her works from control polymers, advances in monolayer doping using graphene 2 process. So Anna, the stage is yours.
Okay, thank you. Okay, good afternoon, everyone. I'm so happy to be here and share with you a story about how we move from controlled polymers to precision polymers with the application for doping of semiconductors. I guess you know that semiconductors are the main constituents of these devices that are inside of electronic devices. The main constituent is usually silicon or germanium, but they are not used as they come. They need to be doped. The doping process consists in the insertion of atoms like phosphorus or boron that have an excess of a lack of electrons in the valence shell, so the conductivity properties of the semiconductor are modified. This process is commonly commonly made by processes like diffusion or ion implantation, but these processes are aggressive and they can destruct the crystal structure of the semiconductor. So lately, new strategy called monolayer doping is proposed. The idea of monolayer doping is using some molecules that will act as a carrier for the dopant atoms. So the idea is that we have a semiconductor and we make a monolayer of these molecules in the surface. After some chemical reactions, it's possible to remove the carrier molecules and the dopant atoms remain in the surface of the semiconductor. This strategy is very interesting because it's a strategy that is controlled and it allows us to move in nanoscale level of the doping of semiconductors. But it occurs in solution, and this is not a good situation for industrial applications. And if I want to modulate the amount of the dopant atom in the surface of the semiconductor, I need to change the molecule. If I change the molecule, I will change the chemistry of the reaction. So again, this is not useful for an industry. So our idea is to use polymers, because in this case, we don't have to change the chemistry of the molecules, but we just can modulate the molecular weight of the polymer and use the chemistry. So for making the grafting 2 process, we use a strategy called grafting 2 reaction. In this strategy, simply described in 2 steps. The first one is a spin coating, when we create a film of the polymer in the surface of the semiconductor. In this case, we eliminate the solvent. And then by rapid thermal processes, we promote the reaction of the polymer with the surface of the semiconductor. The grafting density, that means the amount of the polymer that is grafted in the surface, is described by this equation that mainly depends on 2 variables. The first one is the layer thickness. This reaction, the grafting 2 reaction, as I mentioned before, form a monolayer. It means that if we follow a kinetics of the reaction, we observe that it will reach a plateau, because this is a self-limiting reaction. And the maximum value, the film thickness, the maximum film thickness will be related with 2 times the radius of duration of the polymer. The other parameter, the molecular weight, graphically we can see that from the equation is inversely proportional, but if we compare 2 polymers, one with low molecular weight and one with high molecular weight, we will observe that in the moment the layer is formed by a steric hindrance, the molecules will be organized. So increasing the molecular weight will be referred in a decrease of the dopant dose of the atoms in the surface. The first approach that our group made using polymers for the grafting 2 reaction for the introduction of dopant atoms was by synthesizing a polystyrene with a low polydispersity index. After the polymer were grafted and then eliminated from the surface, it's necessary to make a silicon oxide capping. And the idea of using this strategy is allow the formation of the dopant delta layer, and then by top sim analysis measure the amount of phosphorus atoms that are in the semiconductor. So from the top SIMS results, we observed that decreasing the molecular weight of the polymer results in an increase of phosphorus concentration. If we integrate all these profiles, we will find that the phosphorus does increase. And if we plot it in function of the grafting density, we can see that it's a linear relation. But in this case, we are using a controlled polymers. And recent studies also in our group let us know that sometimes the molecular weight of the polymer before the grafting reaction and the molecular weight of the polymer that is forming the brush is not the same. So we have 3 different scenarios, and we have found that in general, if we have a polymer with a particular molecular distribution, the brush is mainly formed by the side when short chains are attached to the surface. So using this equation in this case is an issue because the molecular weight is not a single number, but it's a distribution of molecular weights. That's why we are proposing precision polymers to try to resolve or be more accurate in the dopant of the semiconductors. A precision polymer basically is a polymer that doesn't have a distribution, but as you can see from this MALDI as an example, is a monodispersed polymer. And the approach that we are doing is by using polypeptides. There are molecules quite related to polypeptides. The difference is that the substitution is in the nitrogen instead of the alpha carbon. This structural characteristic make them soluble in organic solvents as they cannot form hydrogen bonds. On the other side, they can be synthesized by solid phase synthesis. The difference is that we are not using amino acids as units, but we are using submonomers. Submonomers means that if I start the reaction from a amino-functionalized resin, instead of using an amino acid, I am using in the first step bromoacetic acid in presence of a coupling agent, so I can form the amide bond, and then I have an amine that have a lateral chain that is tunable. It means that I can decide what type of amine I can add to my system. So if I repeat this process as many times as I want, I can finally obtain a polypeptide where I control the unit numbers, but also I control the molecular architecture of my polymer. So we use these amines, and at the beginning we tried to synthesize an homopolymer, but we found that it was crystalline, and then to resolve it, we insert these functionalities to avoid the crystallinity. And using this strategy, we were able to synthesize 4 polypeptides with diverse molecular weights. And as you can see from the Malditov results, they were monodispersed, and this technique allows us also to have a reproducible strategy to produce the polymers. Then these 4 polypeptides were grafted in a silicon substrate. We established the optimal conditions, and we found that the film thickness increased in function of the monomer units. Then, by Malditov analysis, we confirm again that if we increase the molecular weight of our polymers, the concentration of phosphorus will be reduced. If we integrate these profiles, we can calculate the phosphorus dose. And from the graph, when we plot the phosphorus dose in function of the molecular weight, we found an inverse relation. But the most interesting thing is that if we compare these experimental results with the expected grafting density of the polymer calculated from the radius of duration of the polymer, we found a perfect match of the values. So as conclusion, we did all the way moving from monolayer, using the technique of monolayer doping, using controlled polymers, and then precision polymers, and we found a strategy that allows to have polymers that are reproducible. We are able to adapt this strategy in an industrial level. We are able to insert phosphorus, so maybe we can say that we are one step closer to the deterministic doping of semiconductors. Thank you for your attention, and thank you to all my collaborators. If you have questions, here I am.
Thank you, Diana, for
we put our phosphorus and our boron in the cell?
Okay, because when you want more operational transistors, you need accurate position of the phosphorus atoms. When you do the typical strategies like laser, thermal annealing, they just make the diffusion when it goes without any control. If we make a monolayer, we are controlling the amount and the position at nanoscale level. So at some point, we are to make transistors and at nanoscale level if we can control the position of the atoms.
Thank you very much.
If there aren't other questions, I have a question for you. So you told that the highest amount of phosphorus in your conductor, you just need the less to improve.
If I want modify the molecular weight of my
Are there any questions? Okay, so many thanks for your presentation, Vivian. The stage is yours.
Thank you very much. Good afternoon to everyone. My name is Davide Perin from the University of Trento, and I'm here today to talk to you about a part of my PhD research concerning the development of intrinsic self-healing matrix for self-healing composites. So before starting, I would like to ask you a question. Why composite materials are so important? In the last year, they have had a remarkable development, and the latest market evaluation stated that the market size value in 2022 was approximately 100 billion US dollar. But the forecast stated that by 2030, this number will go up to 160 billion US dollar. But why they are so important? Because they can be produced and designed in a very agile and streamlined way. If we couple this with a very high strength, stiffness, chemical resistance, fatigue resistance, and high durability, then we understand why this market is so much. But this is the key step for composite material. The key step is the concept of self-healing composite. So let's read together the definition. Self-healing composite aims at the restoration of a lost functionality in a specific application in order to extend the service life of the whole system. So, for the lack of time, I will focus myself on the intrinsic self-healing matrix. This intrinsic self-healing matrix is composed of high mechanical properties, together with a so-called healing agent that is capable of melting or softening at low temperature and possess a high flowability. So, now let's imagine to have a product that upon usage has been damaged. So if this product was made by self-healing material, then through an external stimulus such as an increase in temperature, we are able to soften or melt the healing agent, and therefore we are able to fill the crack. So the aim of my work was the development of this intrinsic self-healing matrix, the optimization of these blends, and then the study of the healing mechanism. As a matrix, I selected polyamide 6, which is one of the best technopolymer. As a healing agent, I selected cycloolefinic copolymer, and as a compatibilizer, I selected polyethylene coglycidine acrylate, aka EGMA for the friends. I blended everything inside my compounder, then I granulated and not pressed for produce the slabs for further characterization, and in this way I obtained several slabs with increasing amount, fixed amount of COC, and increased amount of the compatibilizer. The compatibilizer selection was pretty tough. I selected 5 different compatibilizers, I studied everything, but the best one was EGMA, because this compatibilizer is able to actually chemical react with polyamide 6 and have the possibility to react to create the so-called chain entanglement with COC. This particular interaction goes by the name of asymmetric interaction. It is quite fundamental for self-healing polymer, because this interaction does not hinder the flowability of the cyclic olefinic copolymer. Switching to how I evaluated the healing efficiency, I performed 2 different types of tests, fracture toughness tests, one in quasi-static mode and the other one in impact mode. So one 10 millimeter per minute, the other one 1.5 meter per second. By evaluating the K'(C) of the virgin material, then I heated everything inside the oven in an iron vise with 0.5 megapascal of pressure at different temperature, and then I retested, obtaining therefore the K'(C) of the healed specimen. By the ratio between these 2 K'(C) is the so-called healing efficiency. So moving to the experimental results, here I reported the K'(C) of the quasi-static tests. And it is possible to see that by increasing the compatibilizer content and by increasing the healing temperature, the K'(C) of the healed specimen tends to increase. And if we take as a reference the healing process performed at 160 degrees C, we can see that without the compatibilizer, the healing efficiency was nearly 12%. But thanks to the addition of the compatibilizer, 5%, we increased the healing efficiency up to nearly 38%. But the situation changed dramatically in impact mode. By increasing the content of compatibilizer and by increasing the healing temperature, we were able to increase a lot the so-called healing efficiency. And as a reference, the process performed at 160 degrees C, we obtain, without the compatibilizer, an healing efficiency of nearly 57%, and with the compatibilizer, we obtain a healing efficiency of approximately 82%. That is remarkable for this polymer. But let's see why there is such a difference. For understanding this, I performed fracture photography analysis, and here I reported the fractured surface before and after the healing process in quasi-static mode. And it is possible to see that without the compatibilizer, we have a lack of adhesion between the domain of COC and the matrix of polyamide 6. By introducing the compatibilizer, the fracture morphology changed dramatically from brittle, from that one, to a severely plasticized. Therefore, upon healing, the COC was actually able to flow inside the crack, but was not able to completely fill the crack because the specific surface area developed during the fracture process was too high, and therefore the healing process was not as effective as in impact mode. And in fact, in impact mode, the surface was brittle, was more, let's say, planar, and in this way the COC was actually capable of flowing in a better way and therefore filling in a better way the whole crack. So in conclusion, we succeed in developing this matrix. Without the compatibilizer, we reach like poor healing efficiency, but thanks to the introduction of the 5% of compatibilizer, we reach healing efficiency of nearly 38% in quasi-static mode and nearly 82% in impact mode with an healing process of 460 degrees C. But what about the future? The future is that in the last couple of months, we develop, thanks to the collaboration with the University of Pisa, a self-healing polymer composite made with short carbon fiber. Through injection molding, we were able to produce this huge tensile test, this huge 1A specimen, in order to produce to test with fatigue testings, in order to better understand the healing mechanism in not a macro damage, but in a micro damage. And together with Professor Pietro Russo, we successfully produced thin films, and by film stackings, I were able to produce laminates, which will be eventually characterized and tested with fatigue testing in order to better understand the evaluation of the damage inside the matrix and not a dramatic damage as a K'(C). So thank you very much for your attention.
Davide.
Have you ever tried
laboratory? It has a small size of material, like 50 grams per size. But this was the best option for us because we have also a monoscrew, a bi-screw extruder, but the residence time is too low. We are talking about 30 seconds to 1 minute. The time here is mainly dictated by the reaction because once we add polyamide 6, of course, everything. But once we had the compatibilizer, we need actually to give him the time to react. So 5 minutes was the bare minimum in order to stabilize the torque inside the compounder. So that's why I selected this. In Pisa, before going to Pisa, I produce everything with my compounder, and then I go to an industrial extruder that produces like 20, 25 kilogram per hour. That's the rate. But in that case, the residence time was 30 seconds. So I had to have the material just ready to use, ready to process. So that's why I selected this one.
Thank you. First of all, can you use the compatibilizer for other systems other than polyamide? For the question is if you use the same compatibilizer for different types of polymer.
Okay, yes. Actually, we use different compatibilizer with PCL. We produce the same, so polyamide 6 PCL, and we use IMA, which is anhydride maleic anhydride plastic, and it was actually very good because this covalently bonded, like Giorgini said. So this is a pretty strange behavior of this compatibility. So it's not the optimal one. The optimal one for these blends was polyethylene with maleic anhydride. That had the best mechanical properties, but I hindered the flowability of the polymer. But of course, this plus the big sister of one of the best for this specific application.
For the presentation, also me, a curiosity. Have you some insights how the process is going on? Because I think that you have a polymer that maybe is cross-linking, so you polymer.
You see the huge domain, huge COC domains, totally debonded with the matrix of polyamide 6. When we actually perform the healing process, we increase the temperature. The COC is totally amorphous, so above 100 degrees C, it starts flowing slowly, but it starts flowing. So at 160 degrees C, you are actually giving a lot of energy, so it is able to flow slightly. By keep in touch the surface, the damaged surface, you are able to soften in the polymer. This polymer will go inside the crack. And here you see, like, it's actually capable of producing a layer, but part of the morphology is totally the same. In impact mode here, in the 160 and 180 column, you see the layer. You are able to see the layer. So the COC domains are and you have a layer, a thin fins.
So the self-healing, it's only the that flows into the crack. So you don't have no more the same polymer before and after the self-healing.
It's the same polymer, but
concentrated in
in the morphology.
Okay, thanks.
So we have Edoardo Podda and his work on amphiphilic star-shaped copolymers has viscosity index improvers for lubricants. So Edoardo, the stage is yours.
Thank you. Good afternoon, everyone. In this work, that is in collaboration with NESPA, we study the synthesis and characterization of a star-shaped amphiphilic copolymer to be used as viscosity index improver for lubricant applications. Lubricants play an important role in minimizing friction between sliding parts, prevent mechanical failure, and improve the energy efficiency of the engines. Modern lubricants are composed of a base oil and different additives such as pour-point depressant, rheological stabilizer, and viscosity index improvers. In particular, viscosity index improvers are polymeric additives that have the role to counteract the strong decrease in the viscosity of the base oil as the increase of the temperature. This is very important, for example, in automotive application, because the lubricant must be able to work in a wide range of temperature due to the environmental conditions. However, this is not enough, because during the lubrication, this type of polymeric additives can have a permanent loss of viscosity due to the high shear stress.
We use star copolymers because it is well known that due to their globular structures, they have a great shear stability than the linear ones. Star copolymers represent a particular macromolecular architecture in which we have linear polymeric arms that are covalently linked to a central core. And there are two main approaches to obtain this type of architecture. The first one is the core-first technique, in which polymeric linear arms are grown directly from a multifunctional nucleus. And the second one is the arm-first technique, where the performed arms are linked together by a cross-linking reaction. We choose arm-first technique because it allowed a better control over the structure, the molecular weight, and the distribution, the weight distribution of the samples. In particular, we use a technique named raft technique, and we develop a two-step process. In the first step, we dissolve a mixture of hydrophobic monomer in an organic solvent. We disperse an hydrophilic monomer by the aid of a surfactant, and we use a raft agent. At the end of the first step, we can obtain a polymeric linear arm that are cross-linked together in the second step to obtain the star-shaped copolymers. To obtain a material that can be employed directly in an industrial application, we have to fulfill some constraint. In particular, the solvents must be the same of the final formulation of the product. We use the reagent without any kind of purification, and both reaction steps were performed subsequently in the same reaction vessel without any purification of the performed arms. Through JPC analysis, we can observe the formation of a star copolymer. In particular, at the end of the first step, we have a narrow weight distribution peak at a low molecular weight. And at the end of the second step, we can observe a second peak related to the formation of star copolymer. Using this technique, we can calculate star conversion and the number of arms. We first optimize the synthesis of polymeric arm, and as you can see, the molecular weight increased linearly with
the expected parameters for this kind of reactions. Then we try different optimize different parameters for the synthesis of star-shaped copolymers. Here I report the main cross-link amount. In particular, we also that increasing we have an increase in the star conversion, and we observe the same behavior with the complex viscosity. Then, to increase the star conversion, we want to avoid the reversible termination at the end of the first step. So we try to optimize the ratio between raft agent and the initiator, and we observe that the best result we obtain when we use a ratio at 2.5 to 1. So combining this experience, we try in the ENI laboratories to make a scale-up of this reaction. So we realize 3 batches of about 300 grams and 2 batches of about 10 kilograms. And we observe that for an industrial application, this reaction have a great reproducibility. So in conclusion, we can affirm that inverse micellar polymerization has proven to be efficient to generating star-shaped amphiphilic copolymers. We observe that increasing the cross-linked agent amount, the star conversion and the viscosity increase. And the scale-up of this reaction give great results and greater reproducibility. So thank you for your...
Thank you, Eduardo, for your nice presentation. Okay, I have one. I would like to ask you if you tried also other craft agent and if you your company.
But it gives a red color to the product. For part of is
we have finished our session of today. Now it's
So welcome back. I hope you enjoyed the coffee break. And now we are able to start the second session of today with lunch, with a presentation titled Composite Layers of Polymers, Brushes and Nanoparticles. The stage is yours.
Okay, hello from my side. I'm from and I want to talk about composite layers, and therefore I want to start with the definition. A composite layer consists of at least two layers that are phase separated, and one example therefore is carbon fiber reinforced concrete. And there are engineers in Dresden who built this building, and they were able to achieve wall thicknesses like 2 inches, and there's even a twist in the building. And on a much smaller scale, one could use silicon nanoparticles, for instance, and incorporate them into polymer brushes and achieve a composite layer, but on nanoscale. And my synthetic route to achieve this is to start with initiator-coated substrates and then perform surface-initiated copper-mediated controlled radical polymerization with a cationic monomer to achieve cationic polymer brushes. And those cationic polymer brushes can then interact with negatively charged particles to form a composite like I explained at the last slide. And in a subsequent step, high heat can be used to calcinate, which means to remove all organic compounds, which then results in a porous layer of the beforehand embedded particles. And this layer can be characterized by the porosity. The surface-initiated copper-mediated controlled radical polymerization I mentioned on the last slide is shown here. And therefore, just another, the copper source, the copper plate, which is fixed at a distance to the substrate. And with that, in a facile way, thick polymer brushes can be achieved, like 180 nanometers in 1 hour. And with photolithography, even structured brushes can be achieved. And in the first step, I did the reaction with my standard monomer, which is shown above, 2-methyl oxyethyl trimethyl ammonium chloride, and I achieved porosities of 43%. And in the next step, I then changed to an acrylamide and also used an acrylamide. And I was able to show that even by just changing the polymer, the parameters of the achieved porous silica layer differs a lot. In the next step, I was interested in the use of zwitterionic polymer brushes, because those can be applied to different substrates and don't have swelling behavior like the cationic brushes. And therefore I used SBMA as well as MPC. And I was also able to perform the reaction with those brushes. And after that, I was interested in tuning the grafting density. And this could be done by changing the distance between the substrate and the copper source. But another way is to degraft. And therefore, I use tetrabutylumonium fluoride, which breaks the silicon oxide bond, which anchors the polymer brushes to the surface. And I then did a small setup to get time-controlled degrafting. And with that, I was able to achieve, on at least SEM, very homogeneous looking results that, as you can see on the right-hand side, show a tendency of reduced layer thickness with interaction time. In addition to that, I also studied the influence of the incorporation time. So I used different concentrations of the particles and different incorporation times. And as you can see, the thickness ratio between before the reaction and after the reaction raises with time, which is, of course, what you would expect. But as you can see here, the porosity strongly depends on the concentration. And this slide shows that just by changing the concentration of the nanoparticle solution, very different porosities can be achieved, which means that the process can be tailored to the demands of the customer. And to show that this is not only limited to silica particles, I also used gold particles. And when I did this at first, I was getting those blobs of gold. And if you look closer to them, they show almost crystalline behavior. And this is due to the fact that the melting point of gold is slightly lower than silica and at temperatures of 600 degrees Celsius. And if the gold is small enough, it will just melt, even though it's lower than the actual melting temperature of gold. But I found out that oxygen plasma treatment can also get rid of all the organic compounds, and so oxygen plasma is an alternative to using high heat for the calcination step. And this left me with homogeneous layers of gold that show a certain porosity. And with that, I want to conclude my talk. I showed you that different graphing densities can be implemented, that different monomers can be implemented, that the concentration and the nanoparticle size can be alternated to vary the achieved parameters, and also that temperature and time play an important role. And I showed that the calcination step can be done by high heat or oxygen plasma. And with that, I want to thank you and start the question round.
Thank There's one there.
Maybe I missed something. The application of these materials and how the that you obtain could influence the different applications.
For instance, batteries. They demand a high specific surface area, but if the porosity is too high, they are too brittle. And so they are not stable.
Okay. Compare the samples to measure the porosity. How do you measure it?
Okay, the porosity is measured by ellipsometry. Refractive index of air and silica particles with a refractive index of 1.5. And the refractive index of the porous layer depends on the ratio between those two components. And if one sees it has to be 60% particle.
If the With their presentation, smart recycle-based blended polymers for wastewater remediation, from material design to its absorptive properties.
Thank you for your presentation. I'm Giulia Randa. I'm a PhD student of the University of Messina. And today I will talk you about smart microcycle-based blended polymer for wastewater remediation. Nowadays, we have unfortunately to face with the presence of different contaminants into water and water bodies due to the increasing of the anthropological activities. One of these classes of compounds is represented by organic dyes. Organic dyes represent a serious risk for human health and ecosystems. Wastewater treatment plants have to face with the remediation of such pollutants. On this regard, new filtration technologies are constantly developed to retain these compounds. One of these technologies employ membranes that are polymeric membranes able to retain the pollutants with a sieving process. So, in base of their porosity, they are able to retain the contaminants. The most common polymers employed for the preparation of such membranes are polyether sulfone and polysulfone. As you can see from the same images, they are characterized by very small pores, but they can be easily blended with functional nanofillers or polymers in order to increase their absorption performances as well as the selectivity of the membranes. With this in mind, we decided to study the effect of these two systems, polydimethylaminoethyl methacrylate, that is a polymer sensitive to stimuli such as pH and temperature, and pillarines that are microcycles able to include in their cavity different molecules by host-gas interactions. These polymers already find applications for the preparation of cross-linked polymers or blended polymers for also environmental remediation applications. So we synthesized a pillarine derivative with a brometoxic functionality and pneuma by an RBT-TRP polymerization, and by a simple quaternization of the methylamino groups of pneuma with the pillarines, we were able to obtain a new smart polymer that we named P5Q-pneuma, fully characterized by NMR spectroscopy. Here I showed also just the proton NMR spectra, in which it is possible to observe the proton signals related to aromatic functionalities of the pillarines. Finally, we decided to blend polyether sulfone and polyvinyl pyrrolidone, employed as spore former, with these two smart polymers to obtain, by the non-solvent-induced phase separation process, membranes and beads. This is a very short video in which I show the preparation method of the non-solvent phase separation process. And we prepared different polymeric blends, employing 3 different coagulation baths, properly to study the effect of the pH responsive effect of the pneuma. We characterized all the developed beads by a TRFTR spectroscopy to confirm the preparation of the functionalization of the beads, as well as the same images. By same images, it is possible to observe a change in the morphology of the beads thanks to the different functionalities of the polymeric blends employed. Finally, to test the adsorptive properties of these systems, we preliminarily tested the performances towards the removal of 2 model organic dyes, methyl orange and methylene blue. What you can see clearly is that the bead prepared with the P5-Q-pneuma blend, it's able to retain methyl orange better compared to the others. In order to understand the selectivity of these systems towards one of the 2 dyes, we tested them in a solutions made of both dyes. And what you can see again is that the P5-Q-pneuma based bead is able to selectively retain only the anionic dye methyl orange. This is due to the electrostatic effect of the bead, because it's positively charged for the presence of quaternized amino groups, but also protonated amino groups for the acidic environment of the coagulation bath, but also to possible host-guest interactions between the pillarines and the methyl orange. We of course, studied better the absorption performances of all the beads, employing UV measurements and a 20 milligram per liter solution of methyl orange. And again, we can see that the P5 couped based beads demonstrated the best absorption performances. So for these systems, we studied the effect of the time, the quantity, different concentration of methyl orange to understand the absorption kinetics and the absorption isotherms and the models that better define its behavior. We went deeper and studied the post-functionalization of these beads, employing 1,4-butansultone to obtain a zwitterionic bead. This zwitterionic bead is able to retain both anionic and cationic dyes, and it's able also to be regenerated, but we did just the first preliminary tests on this. So this is the mechanism towards the removal of both dyes by the zwitterionic bead. So again, possible host-guest interaction and electrostatic interactions between the beads and the dyes. In conclusion, we were able to obtain different functional beads, fully characterized also by XPS measurements, and we were able to perform different absorption experiments to understand their absorption behavior, confirming that the P5 couped based beads was the best one for the retention of the anionic dye methyl orange, as well as a zwitterionic bead able to retain both anionic and cationic dyes. Are currently in progress the study of other systems for the filtration and removal of other contaminants from water. All of these are...
So if we reach the same conditions, it's good because we are synthesizing material that's much more flexible and are capable of conducting much more ions. So if we achieve the same resistance, is the ideal.
Thank you.
Are there any other questions? Okay. Best reaction conditions.
You mean for draft polarization?
Yeah.
So when we analyze the kinetics, we see conversion over time. Based on that, we can establish the amount of monomers, the solvent, concentrations, everything that we must use to perform the best reaction. And since it's linear, this is the best condition that we can achieve, because we can stop wherever you want. So you can determine the condition, and then over time stop, and you know that the molecular weight at the end will be at what you predicted.
Do you have a target final molecular weight?
The final one that was 60,000, okay. That was already read.
Thank you.
Thank you.
Okay, we have another one.
Hi, I'm here. Thanks for the nice talk.
Thank you.
I was wondering, because most of the actors also in the units that you show in the schematic images are made by layers, different type of compounds.
Which slide is that?
The introduction before you was displayed like this. Like a polymer, the image.
No, basically the fit phase, and this is the so the most important here is that by controlling the molecular wave, you can control the morphology. Okay. So you can have spheres, cylinders, lamellar, basically by the size of the blocks. Because, for example, if you imagine if they have the same molecular wave, for example, the interface between them will be flat. In this case, we have a lamellar. So as soon as you start to increase one of the molecular wave, it starts to overlap. making cylinders, and finally spheres.
And do you expect different behavior in the movement? Like,
Yes, the lamellar morphology by literature. Blocks.
Nice, thank you.
Welcome.
Okay, so we are again. With the metal polymer, nanostructure materials for catalytic water treatment in mild conditions. The stage is yours, Stefano.
Okay. I'm Stefano Scuti, PhD year, third year of the University of Bologna, and today we've been talking about hybrid polymers, nanomaterials, employment for catalytic water treatment. Before to start to present my results, I want to watch the picture. You ever seen that? It's the picture won the environmental photographer of the year in the 2016. It's the prize for Guardian. It represents, for me, the strange of the environmental pollution. Environmental pollution from the air pollution toward the water pollution. And regarding the water pollution, the persistent organic pollution represent one of the most important toxic, harmful systemic compound present in the water media. Especially nitroaromatics compounds was defined by the Environmental Protection Agency from the USA and the ECA, the European Chemical Agency, for a toxic compound for human and biodiversity. So different strategies was developed to transform this type of compounds in added value chemicals. Today I want to talk about the transformation of the nitro groups into amino groups in order to form the added value chemical and with the aim to insert them in the industrial cycle. But which is the material that we've chosen for that? We have chosen the colloidal nanoparticles. We know they are a fascinating system because their properties are strictly related for the size of the material, especially for the catalytic point of view. But they are characterized by the thermodynamical instability. So it's necessary to adopt a different strategy with the use of the polymeric stabilizer to enhance their stability. The employment of polymeric stabilizer have, first of all, a steric effect to limit and improve the stability and therefore a loss of their peculiar characteristics derived from the nanometer dimension. But in the other hand, we have an electronic effect derived from the interaction between the polymer matrix with the surface of the metals. Therefore, we have a sort of modification of the charge density of the metal derived from the polymer presence by a different type of interaction, weak and strong interaction. So if the presence of the polymers can be so strong for the design of this type of materials, why we can move toward hybrid materials? Hybrid materials, I mean, why we can immobilize the metal nanoparticles in the 3D polymeric structure like a gel system. And we have chosen to focus on the cryogels. Cryogels as suitable materials obtained by cryopolymerization. Cryopolymerization is a reaction conducted at the temperature below the freezing point of the solution. And during the freezing point, we have the growth of the crystal, the height of crystals inside the structure, and the thawing phase, the crystallite mass, and therefore we have the porosity at the end of the materials. And therefore we have a sort different properties derived of these types of materials. But in particular, we have prepared 3 types of cryogels with 3 different acrylic-based monomers characterized with several functional groups with the presence of oxidryl, amine, and acid groups by a cryopolymerization reaction in the presence of a cross-linking agent to obtain the cryosponges. It was characterized by the scanning electron microscopy, thermal analysis, and spectroscopy to confirm the material obtained. And
at this point, we have, by in situ approach, we have an impregnation of the metal precursors, in this case, the gold and palladium precursor onto the polymeric matrix, and then by a reduction step, we obtain directly inside the polymeric structure the nanoparticles. The system was characterized by XPS spectroscopy to confirm the presence of the metal species inside the system, and the TEM analysis to analyze which is the dimension of the system. We have obtained very fine nanoparticles in the range of the 5-10 nanometers. So at this point, we have tried this type of material for the reduction of nitrophenol to aminophenols in presence of the sodium borohydride. The sodium borohydride is hydrogen carrier to form hydrogen inside the system. It's a redox catalytic reaction, but we can follow this type of reaction by UV visible spectroscopy, and therefore correlated the absorption peak of the nitrophenol produced during reaction with the kinetic performance, and therefore we can evaluate which is the properties of the final materials. Compare the results obtained. Firstly, we have compared two different metals, so gold and palladium, and we can observe like palladium-1 system is the most exhibit most performance than the gold, because the palladium is a typical system for hydrogenation reaction. But the most peculiar system was observed for when we have compared the type of the polymers that we have used to immobilize our nanoparticles. In particular, we can follow the slide and the system with acrylic acid. The acrylic acid moieties represent the most active system. Why? Which is our first question. Analyze the mechanism we have observed, like the acidity of the system can influence the hydrolysis of the sodium borohydride inside the system, inside the catalytic mechanism, so each step pH dependent. To confirm which is the effect of the functional group, we have analyzed by a titration in function of the theta potential to observe which is the real surface charge at the pH of the reaction, and the only one sample that exhibits a negative charge is the system with acrylic acid monomers. So, when we have a pH upper 5.5, we have the protonation of the acid moieties to form an acid microenvironment around the nanoparticles, and therefore they contribute directly with the catalytic mechanism to increase the sodium borohydride hydrolysis, therefore hydrogen production, until to increase the nitrophenol conversion. So, at the end, the most important thing at the end of this work is we have observed a synergic effect to the polymers and metal nanoparticles until to have a novel hybrid system with the aim to produce a novel hybrid catalytic system to have an increase of the nitroaromatics conversion in the water media. I'm finishing. I want to thank all guys that work with me and my research group. Thanks for your attention.
Questions? No one? Ah, there is one.
Thank you for a very nice presentation. Your systems are porous. The sizes of your pores.
Good point. We have a problem to evaluate the porosity of the system. Carried out the BET analysis, it's necessary to have a sample with the dye densities. But this type of the cryogel, it's a very low density, so it's so difficult to. Sorry. Okay. Oh, bad. So it's difficult to analyze that with the analysis by indirect methodology.
Could be, I mean, like estimate your.
With the that maybe the morphology connected allowed to have a very
Okay. Entitled Self-Healing of Functionalized Interfaces Made of Polycrapolactone-Coated Glass Fibers for Composite Applications.
Good morning, I'm Laura Simonini. I'm a PhD student from the Department of Industrial Engineering in Trento. And today I would like to talk about interfacial healing in structural composite. So we know that a fiber-reinforced composite is made by matrix and fibers, and between these two there's a region that is called interface, where matrix and fibers can interact. We know that fibers are much stronger than the corresponding matrix, so it's very important that when a stress is applied to the composite, the matrix should transfer this stress, this load, to the fibers. And this can only happen if between fibers and matrix there's a good interfacial adhesion. So interfacial adhesion is dictated by different interactions such as macromolecular diffusion, chemical bonds, electrostatic attraction, or frictional contribution. But when this stress that is applied to the composite reach a maximum value, so this interaction can't withstand anymore this load, we have the bonding. The bonding is when, so the fibers and the matrix detaches from each other and they don't communicate anymore, so we don't have the stress transfer from the weak matrix to the strong fibers. And this leads to the catastrophic failure of the composite. So how we can evaluate this adhesion at the interface? We have several methods that are named as microbond tests, that are experimental methods in microscale for studying this interfacial adhesion. And today I would like to stress more on microdebonding test. This test, the one that is here schematized, from this test we have the position of a single drop of matrix on a monofilament of fiber. Then here we have also video. In this video, this device is taking the dimension of fibers and droplets, then two blades come and reaches the drop of matrix, so a shear stress is applied to the, at the interface. It reaches a maximum values where we have the bonding. So once we take this value, that is this one, and divide it for the embedded area, so the dimension of fibers and droplets, we can calculate the interfacial shear strength. That is the measure of adhesion between fibers and the matrix. Now, how can we improve this adhesion? We can have several methods based on the fiber surface modification. And in this presentation, I would like to stress on the position of a polymeric coating. So the idea is this one schematized in the slide. So we deposit a polymeric coating like graphene or physical deposition, and what we are increasing is the entanglement between the polymeric coating and the surrounding matrix. But this polymeric coating can also impact other functionality to the composite, and in this case I would like to talk about self-healing. Why? Because once we want to delay the bonding, we want also to prevent its propagation. So we know that self-healing system can be divided into extrinsic and intrinsic, but the one that we are interested in is intrinsic. Why? Because they are reversible physical or chemical interaction So multiple healing can be applied at the interface. The idea is this one, so the application of a thermoplastic coating on the surface of the fiber. So the aim of my work is to tailor the interface to fully exploit the potential of a fiber-reinforced matrix, composite, and for doing this, we deposit a PCL coating on the surface of the fibers to improve both interfacial adhesion and providing self-healing capabilities, so to delay the bonding and to prevent its propagation. We started from materials such as epoxy matrix as epoxy resin for the matrix, glass fibers for the fibers, and polycaprolactone as the interfacial healing agent. We dissolved PCL in DMF and THF to obtain a liquid solution of PCL, and then using this particular device that was developed by Fibrobotics in Finland, we take just one drop of this liquid PCL and we forced one single fiber to pass through the liquid PCL in a unidirection with different coating speeds. So the idea is the one schematized here, so we want to obtain a coating like this, that is a sort of sizing. So from the morphological characterization, we can see that the position of this layer is very homogeneous, very compact, and also consistent. And we can see that there's the relation between the coating speed and the thickness of this coating. From this analysis, we selected just one of this combination, the best that we supposed that is. So we did the mechanical characterization. So we applied the microbonding test for the calculation of the interfacial shear strength. From this test, we obtain a huge amount of data that are here reported. We see that from the linear regression of all of these points that are in a graph where there's the load and the embedded area. So the slope of the linear regression is the interfacial adhesion. We evaluated a plus 23% of increase of the interfacial properties comparing to the uncoated fibers. And again, from microdebonding test, we can evaluate also the healing efficiency as the ratio between the adhesion properties before and after healing. So, okay, still from this set of data, we evaluated the healing, providing the healing by placing the samples in oven. And we obtained at the first healing cycle 100% healing efficiency. So we were able to fully repair the interface. Then we did also other 2 cycles of breaking and repairing, and we obtained 0.5% of 50% of interfacial healing. So in conclusion, we were able to tailor the properties of the interface between epoxy matrix and glass fibers by fiber surface modification to increase interfacial adhesion and to provide self-healing capabilities. We did this by the deposition of a polycaprolactone coating on glass fibers. We obtained an homogeneous coating, an increase of 23% of the initial adhesion, and a fully repairable interface at the first cycle, 50% at the next cycles. The next step will be the modeling of this behavior. So we want to model the distribution of the stresses along the interface to have a fully, a better understanding of the role of the surface modification, so the role of its coating. And this will be done in collaboration with Tampere University and Fibrobotics from Finland. So thank you very much for your attention. I'm available for questions.
Thank you. Let's go with questions.
Thank you for your very nice presentation. I would like to ask if you tried also other polymers for your coatings or all other of the polycaprolactam.
Actually, no. We just focus on the use of PCL because we saw from the literature that is promising polymer used as healing agent at the interface. Okay, we saw that they use at so we focus on this.
Okay, thank you.
Are there some other questions? We have not time, but okay.
Did you increase compatibility?
Yes. Yes. For time reason, I just show. Is based on research and other possibility to improve other mechanical, physical, and chemical parameters.
Thanks.
With a presentation entitled Development of Superabsorbent xanthan-based hydrogel composites for forestry and agricultural application. You can go.
So, good evening, everybody. As I said, I'm Alessandro Sose from the University of Trento, and today I will talk about hydrogel composites for forestry and agricultural applications. So my PhD activity is part of an European project called One Forest, founded by Horizon 2020 program. And the main aim of this project is to finding solution, technological advancement for forest management and for silviculture. One of the most important problems that is putting forest at risk is the water scarcity. Because we all know that in Italy, but also in Europe, the rainfall are less and less common, and therefore there is the need of finding something to help to promote the growth of the plants during the first years of life. So the role of the University of Trento in this project is to develop two products, both biodegradable and wood-reinforced composites. The first is called soil conditioner, and is a product which is put near the roots of the plant. As you can see from this schematization, it should absorb the water during precipitation, store the water, retain it, and release it slowly during dry season, so that at the end the plant can survive under drought conditions. The other product is named topsoil cover, is a sort of mulching film, and the main aim in this case is to prevent the growth of competing weeds, because they can suffocate the plant, and also it should reduce the water evaporation from the soil, but at the same time it should allow the rain to reach the plant's roots. So nowadays most of the mulching film are made of plastics, like polyethylene, polypropylene, and so they are not environmentally friendly. So instead we select a bio-based material, biodegradable material, which is xanthan gum, which is characterized by high water absorption capacity for both the production of these two products. And we developed a method which is very simple for the production of both materials. In case of soil conditioner, we simply mix the xanthan gum and we add the cellulose fibers in water, so the end to have an homogeneous mixture. Then after drying and milling, we can have a powder which is very easy to be handled by anyone. And after preliminary analysis, we found that the best ratio xanthan to fibers is 2:1. Then for the topsoil cover, instead, starting from the same mixture, we found the importance of adding a cross-linking agent, because after thermal treatment in oven, we can have a material which is stable in water, so when it rains, it doesn't dissolve, but remains there with a certain consistency and shape. So now I reported just very briefly the results, most the practical ones. So what about the soil conditioner? We studied the effect of this material on soil. In particular, we used this sample with, I reported the result also only of this sample, which is characterized by this ratio, xanthan to fibers. And about the maximum water holding capacity, which is the maximum water that the soil can absorb before reaching saturation, we found good results just by adding small quantities in weight of our material. And we also found better result with respect to a commercial product, soil conditioner, which is a superabsorbent polymer based on potassium polyacrylate. Also, we investigate if the water can remain in the soil. So we measure the water retention. And we found also in this case good results for the amount which is less than 2% in weight respect to the soil. Also then we made a practical application on grass. We just planted grass seeds in the soil, and we found that in our with our material, the plants could survive also under drought condition, so without water. And also we compared the material with the commercial product also in this case, and we found better results in terms of germination rates, which is the ratio between germinated seeds to planted seeds. About the topsoil cover, we made a scale-up version using citric acid, which is a natural cross-linker. We studied the effect of the thermal treatment of the material. So we developed two products, one not cross-linking in oven, and the other one cross-linking in oven at 165 degrees C. And we planted tomato plants because they are very easy to be cultivated by anyone. It is a sort of accelerated test to assess the feasibility of this material in a practical condition. This is how we install the material at the base of the plant. But the most important thing is that after 80 days, in case of not cross-linked material, so not thermal treatment, the material dissolved, degraded. Instead, in the other case, we have a better response, an increase of durability, and a partial protection of the weeds, respecting the other two cases. So to summarize the results, the two plants with the topsoil cover grew better. We have a partial protection from the competing weeds in case of cross-linked material, but we have some drawbacks regarding the shrinkage because the material was cyclically stressed by water absorption and desorption. At every desorption, there was a shrinkage. And also we have problems with the flexibility. So we optimized the composition. We add glycerin as a plasticizer to increase flexibility. We changed the type of fibers. We use wood fibers so to have longer wood fibers, so to have a skeleton to reduce the shrinkage. And we test different cross-linking agents, also sodium thiomethophosphate and tannic acid. We test the material at 3 different conditions of temperature, and we put the materials in water to evaluate the water uptake and the swelling degree. And we found that in the first 2 cases, at low temperature, the material dissolved after a few days, but at T2, so 165 degrees C, the material resists in water, and in particular, we performed the test cyclically, multiple times, and for citric acid, we have the best response with material which is never dissolved in water. So we have a good water regulation of the material. And so from this test, we can say that the thermal treatment is necessary. And finally, we also measure the water permeance, which is water vapor permeance, which is the permeability normalized on the thickness. We compared with a commercial product, which is a commercial polypropylene matching film, and we also in this case found good results for the citric acid, which are very similar to the commercial product. So finally, we have developed a simple, scalable method quite inexpensive for the production of both material that can be used in forestry and agriculture to regulate the water properties of the plants and to increase the survival rate of the plant under drought conditions. So I would like to thank the project partners of the One Forest project and you for the kind of attention.
Are there some questions? There's one there.
Thanks for the presentation. Very nice, interesting, and actual topic. I really enjoyed it. But one curiosity, the fact that all these materials are bio-based, flows, and it doesn't affect the stability of the material in the biodegradable part. Like it stays in the soil for how much time, and or it's on for the
we found that most danger of the life of a plant. All the topsoil cover have add the cross-linking with problems. This insects that now the life of life of just other cross-linking agents and yeah, other, yeah, to reach for
the gravimetric.
Yeah, vulnerability.
Okay. Alessandro. With a presentation called the Malin effect, a study on the development effect on the fractal behavior of
Thank you. Good afternoon. Today I will present my results about Mallin's effect reversibility in rubber compounds. Rubber compounds are used in different types of objects such as tires, gasket, and also in the sport field such as in bungee jumping courts. These type of materials have a quite complex structure. They are formed by an elastomeric matrix and filler particles. However, filler particles modify chain mobility of the matrix. So we have a gradient of zones with different chain mobility. If we perform a uniaxial tensile test on a dumbbell specimen, we obtain this type of curve, so we can observe a nonlinear behavior of this type of materials. If then we unload the specimen, we can observe lower stresses, and this is due to a dissipative behavior of the materials. At the end of the cycle, we can observe also a residual strain. If we load again the material, we can observe that the stresses exhibited in the second loading are lower than that experienced during the first loading. And this effect is called the Malins effect. And this is a softening induced by the first applied deformation. It's important because in real applications we have objects that are subjected to different loading, so we have to consider the mechanical behavior of the softened material. Different interpretations present in literature about a Malins effect. We have some hypotheses that concern some mechanism related to the interaction of matrix and filler, or just the filler, or just the matrix. And in order to explain what is this Malins effect, some experimental works have been performed in literature, especially in uniaxial tensile conditions. And for example, the reversibility of Malins effect. In fact, as already studied in literature, after a thermal treatment, the softened material can recover the mechanical behavior of the printing material. Here there's an example in which we have reported the virgin and softened material mechanical behavior, and the mechanical behavior of a softened material after thermal treatment, in which we can see that softened material has partially recovered its pristine behavior. This recovery is possible just in some conditions, and it depends on the type of metric and filler, on protection level, and also on the conditions of the thermal treatment that we apply. However, no correlation is present between the temperature of the treatment and the transition and curing temperatures of the materials. And moreover, there's no study in literature about the effect on virgin material mechanical behavior. In fact, we know that if we apply thermal treatment, some further reticulation or chain scissions can occur in the material. So in my work, I have performed an analysis on the effects of softening and on thermal treatment on softening, but not in performing just a uniaxial tensile loading test, but by seeing the effects on fracture behavior of the materials, because we know that these materials are applied in objects that can be subjected to some failures, such as tires and also batch jumping cords. The materials that I have investigated are one HMBR filled with carbon black and one NBR filled with silica. And we have performed the fracture test in different geometries. For example, this that is a single edge notch in tension, and this that is a pure shear conditions. Both specimens have been notched before the testing. And we performed tests with a test machine to obtain the load displacement curve. So at the beginning of the test, the notch is closed, then it opens up to a moment in which the crack starts to propagate. It's called crack onset, and we have evaluated the fracture toughness by these types of formula that are linked to the geometry of the specimens and on the input energy up to crack onset. Moreover, we are also interested in measuring the deformations, local deformations on the specimens. So we have a speckle pattern on the specimen, and tests were video recorded in order to track the displacement of this pattern. This analysis is called digital image correlations. So we have also measured the deformations, the local deformations on the notch plane from the notch tip to the side of the specimen. We wanted to see the effect of softening on the fracture toughness of the material. So we have performed both fracture tests on the virgin material and on a material that has been previously softened. And here there are the results. So on both the two materials we obtained similar results. The fracture toughness of softened materials resulted to be lower than that of the virgin one. And moreover, we've also applied the thermal treatment on the softened material. So we have performed fracture tests on material that was previously softened, and then thermal treatment was applied before performing the fracture test. But how we have chosen this thermal treatment? We have chosen a treatment that could recover the mechanical behavior of virgin material. We have performed this type of test, uniaxial tensile test, and here I've reported the curves of the virgin material, of the softened material, and on the softened material after the thermal treatment. We can see that a good recovery was observed, especially at lower deformations that actually were higher than the deformation experienced during the fracture test. So a good recovery was obtained for both the material. And moreover, we have also controlled the effect of the thermal treatment on just the virgin material. So here I've reported the tensile curves of the virgin material and of the virgin after the thermal treatment. We can see that with this type of treatment, no further articulation was observed in both material. Okay. And here the final results. So we can see that on the first material, after the thermal treatment, the soft material has a fracture toughness that is comparable with that of the virgin material, while on the other material a different result was obtained because the fracture toughness of the soft material after the thermal treatment is not equal to that of the virgin material. We don't know what is the cause of this difference. We have hypothesized that it was due to the fact that recovery was checked on just uniaxial tensile loading conditions, while the fracture test in this case was performed on the same with the same loading conditions, while in this case with a different condition, because this is pure shear loading conditions. Or maybe also the fact that the material is different both in matrix and in filler. So to conclude, on this type of materials in under investigation, we have obtained a good recovery in uniaxial tensile loading conditions, while different results were obtained on the recovery of fracture behavior of the material. And more investigations have to be performed in order to understand what is the cause of these differences.